So today I'm starting to explain about colligative properties. So the presence of a solute in a solvent is going to affect the property of that solution. Some properties are not dependent on the nature of the dissolved substance, but on how many dissolved particles are present. These are colligative properties, and they seem kind of strange at first when you think about it. They're properties that depend not on the identity of the solute, but on the concentration of solute particles. So if you think about that, it's kind of weird because it doesn't matter what the solute is that you're dissolving. These properties are going to be true no matter what the solute is, because it's purely based on the concentration. This is going to be the only time, besides calculating molality, this will be the only time that we use concentration, with molality as the unit, just to let you know. So the first colligative property I'm going to talk about is called vapor pressure lowering. And I think I've already kind of discussed it a little bit. So the boiling and freezing points of a solution are going to be different than that of the pure solvent. A non-volatile solute raises boiling point and lowers freezing point. So those are going to be two other colligative properties. One sec. Frank just came. Okay. To attendance. There he is. Okie dokie. Right. So we have vapor pressure lowering, which is going to affect boiling and freezing points. Oh, why did that just exit? Weird. Weird. Go back. There we go. All right. And a non-volatile substance, which is what we talk about when we're talking about colligative properties in solutions. Basically, they don't evaporate quickly. You can say one that has little tendency to become gas under existing conditions, or you just look at a non-volatile substance as something that doesn't evaporate quickly. So here is a graphic depiction of the effect of adding solute to a pure solvent. You can see that little laser on here. So we've got the pure solvent, which is in black, and a solution. So that means any solute that has been added. And you can see that it lowers vapor pressure because vapor pressure is here. And again, this is a phase diagram. If you remember that phase diagram. So you've got your solid, your liquid, and your gas. So between your liquid and your solid here, this is your melting or freezing, but we refer to it as freezing. So this is your freezing point here, and you can see that it's been lowered. And then up here between liquid and gas, you've got your boiling points here, and you can see that those are elevated, higher temperature, because temperature is on the x-axis. So just reading from the description, the vapor pressure as a function of temperature is shown for a pure solvent, a solution of that solvent, and a non-volatile solute. The vapor pressure of the solution is lower than the vapor pressure of the pure solvent. And we can see that just by the fact that the graph is, these lines are lower for the vapor pressure on the y-axis. Right. This can be seen by noting the decrease in pressure between the pure solvent and the solution at the temperature that is the boiling point of the pure solvent. So they're talking about this line here. So the blue line is lower than the black line, and that is reflective of the vapor pressure. The solute thus reduces the freezing point and elevates the boiling point. So that's going to be the focus for today. To understand why non-volatile solute changes the boiling and freezing point, we're going to look at equilibrium vapor pressure. So remembering that vapor pressure is caused by molecules that have escaped the liquid phase to the gas phase. If I've got my little beaker here, my closed system, and you've got some evaporated molecules that are going to exert a specific pressure on the surface of this liquid, and that is vapor pressure. So vapor pressure can be thought of the measure of the tendency of molecules to escape from a liquid. Now, I do believe what I've mentioned before is if you add solute, and I'll just over exaggerate the size of my solute particles. If you add solute to your solvent, you're going to have fewer solvent particles at the surface, which means you're going to have fewer molecules escaping into the gas phase. And that's why vapor pressure is lowered. So let's use sucrose or sugar as an example. It's going to lower the concentration of water molecules at the surface of the liquid, and that's going to have fewer water molecules leaving the solution, entering the gas phase, and therefore lowering vapor pressure. So if you have pure water, again, I'll do side by side. And here, let's pretend like those are the same size and shape. And I've got, these are my water molecules, but now I'm going to add sucrose. So now I have fewer water molecules at the surface, and that's why vapor pressure is lowered. Oh, okay, guess I had a diagram anyway. So you've got pure water on the left-hand side, and then an aqueous solution of a non-volatile solute on the right-hand side. And you can see that there's just a lower number of particles that escape from the solvent phase to the vapor phase. And so you're going to have a lower vapor pressure in a solution compared to the solvent. Now, it makes sense if we talk about, I'll just delete my drawing since we already have one. So if you think about the fact that a colligative property doesn't depend on what the solute is, only how much of it is, this starts to make sense, because the more purple you add, then the lower the vapor pressure is going to be, because you're just taking up room where generally we talk about water, where water particles are. So this is why a colligative property doesn't depend on the nature of the solute or the identity of the solute. It only depends on concentration. Non-electrolyte solutions of the same molality have the same concentration of particles. Now, this is a really important part. And remember last week when I told you about being able to identify ionic compounds and how they dissociate, and identifying how much ions would be present? This is going to come into play now. That's why we say non-electrolyte solution of the same molality have the same concentration of particles. Dilute solutions of the same solvent and equal molality of any non-electrolyte solution lower the vapor pressure equally. What that means is you can measure the amount of decrease in vapor pressure according to the molal concentration. For example, a 1 molal aqueous solution of non-electrolyte glucose lowers the vapor pressure of water by 5.5 times 10 to the minus 4th atm at 25 degrees C. A 1 molal aqueous solution of sucrose will also lower the vapor pressure by the same amount at the same temperature, because again, a colligative property is only based on concentration in molality, not on what the solute is. So whether it's glucose or sucrose, doesn't matter. It's only based on molality. Okay, that defines it as a colligative property. Oof, I'm gonna move that. Hold on a sec. Why did that get shifted? Okay, let's try that again. All right, so again, we have a phase diagram looking at boiling point. Because the vapor pressure has been lowered, the solution is going to remain a liquid over a larger temperature range, as you can see from the red line there. So you have a larger, like basically you can look at it as if you measure the area of the L section of the graph, it becomes larger. That means it's a liquid over a greater range of temperatures. So it's going to lower freezing point and raise boiling point. I'll talk about each of these separately. Okay, so boiling and freezing point also depend on concentration, so they are also colligative properties. Now, we'll start with freezing point, and we call it freezing point depression. And by experiment, we find that with water, a 1 mol solution of a non-electrolyte solute will lower the freezing point of water by 1.86 degrees Celsius. It is a very specific amount. When 1 mole of a non-electrolyte solute is dissolved in 1 kilogram of water, again, 1 mole of solute dissolved in 1 kilogram, that's equal to 1 mol concentration. The solution will freeze at minus 1.86 degrees and not 0 degrees. That is freezing point depression. This does actually have real life applications, and so that's why we care. If you double the concentration and you have it at 2 moles, the freezing point is going to go down by 2 times 1.86 degrees. So it will freeze at negative 3.72 degrees Celsius. So for any concentration of a non-electrolyte solute in water, the decrease in freezing point can be determined using a value of negative 1.86 degrees per mol. And of course, we can turn that into a nifty mathematical formula. So we have the mol freezing point constant, which is Kf. Remember, K is a constant, F for freezing. That's the freezing point depression of a solvent in a 1 mol solution of a non-volatile, non-electrolyte solute. Each solvent, of course, has its own mol freezing point constant. And so we use delta TF to identify the difference between the freezing point of the pure solvent and a solution. So it's like remember, delta is a change or difference. And then we've got temperature, and that's freezing. So the change in freezing temperature. So our formula that we use is delta TF equals KF times M. Delta TF is the change in freezing point. KF is the mol freezing point constant. And of course, M is molality. Kf is expressed in degrees C per M. Well, like I said, it's 1.86, negative 1.86 degrees C per M. That is a constant as reflected by the capital letter K. And M is moles per kilogram. So example, what is the freezing point depression of water in a solution of 17.1 grams of sucrose and 200 grams of water? And then what is the actual freezing point of the solution? So first thing that we do is we change this to moles. That's why I always tell you the first thing that you do when you see grams, change it to moles, because grams are not useful, moles are useful. And your 200 grams of water, you're going to want to make into kilograms. And then you're going to use your delta TF equals KF times M formula. Now, when they say, what is the freezing point depression, that they're talking about delta TF. And then what is the actual freezing point of the solution? It doesn't matter so much for freezing point depression because freezing for water is 0 anyway. So whatever delta TF is, that will be the same as the actual freezing point of the solution. It's going to be a little different when I talk about boiling point elevation. So we're given the solute mass and chemical formula. We're given the solvent mass and identity. What we don't know is freezing point depression first, and 2, the actual freezing point of the solution. So here's the plan. We're going to change the mass of the solute using molar mass to get the amount of solute in moles. We're going to then calculate molality, and then we're going to use delta TF equals KF times M. We're going to find the freezing point of the solution by adding the freezing point of the solvent plus delta TF. Again, for water, this number here is 0. So whatever delta TF is, that will be the new freezing point for the solution, right? That's why we use the word solvent versus solution. So let's go ahead and calculate. We've got 17.1 grams of sucrose. The molar mass by adding up all of that is 342.34. That means we have 0.05 moles of sucrose. Now we're going to put that over our 200 grams of water. We're going to convert grams to kilograms. So we get 0.25 moles per kilogram. That is a concentration of 0.25 molal. Everyone with me so far? I'll assume that's a yes. Next, we're going to use the formula, put that back up here, delta TF equals KF times M. So here is our KF, that's our molality. You notice that molality cancels, which gives you only the unit degrees C left over. This is a constant, negative 1.86. So the answer to question A, what is the freezing point depression? It is negative 0.465 degrees C. For question 2, what's the new freezing point of the solution? Again, water freezes at 0. So whatever your delta TF is, so is your new freezing point, as long as you're talking about water, which is pretty much what we do anyway. Okay, let's do a couple more. A water solution containing an unknown quantity of a non-electrolyte solute is found to have a freezing point of negative 0.23 degrees C. What is the molal concentration of the solution? All right, so now we're given different information. We're still going to use delta TF equals KF times M, but this time we're given delta TF. Of course, this is constant, and they're asking for M. So you can rearrange the equation to solve for your unknown. M equals delta TF over KF. And that's going to equal minus 0.23 degrees C over negative 1.86 degrees, C per M. So these degrees C cancel. Because this is a denominator of a denominator, it actually goes up to the numerator, which gives you the unit that you need, and you just plug into your calculator and you should get 0.12. Sorry, my 2 looks like a 7. It should be 2. Okay, another one. A solution consists of 10.3 grams of the non-electrolyte glucose, C6H12O6, dissolved in 250 grams of water. What is the freezing point depression of the solution? So this is a lot like the first question. So I've got to change this to moles, make that into kilograms, and then use delta TF equals KF times M. So I got 10.3 grams times, that'd be 1 mole. And I do believe glucose is 180, but just in case, getting out my calculator. You've got, turn that sideways. All right, so you've got 12 times 6 plus 12 plus 6 times 16, yep, 180. That's all. There's a few molar masses that you might want to remember if you take entrance tests, because they're compounds that are used quite often on exams. So one of them is glucose, 180 grams per mole. Water, of course, is 18 grams per mole. Those are pretty easy because they're like, you know, a factor of 10. The other one is carbon dioxide, and that's 44. I think those are the three most commonly used molecules. All right, anyway, so we cut that and get the calculator out again. And you do 10.3 divided by 180, and you get 0.57 moles. I'm going to put that straight on 0.25 kilograms divided by 0.25. Oops, put that in around 0.57 divided by 0.25. And I get 2.28 for my molality. Then I go up to my equation here. Bring that down here. So delta TF equals negative 1.86 degrees C per molal times 2.28 molal. So that cuts. And it is asking me for freezing point depression. So it's not asking me for a new freezing point. So I do 1.86 times 2.28, and I get negative 4.24 degrees Celsius. That is my freezing point depression. Did I do that wrong? Seems so. How did I get that? 10.3 divided by 180. Oh, that's what I did wrong. 0.057. All right. So then that's going to be 0.228. 0.228. I was off by, I forgot a zero. So this is, anyway, it's this. All right, I'm going to give you, let's say a couple minutes to do this one. Okay, boiling point elevation is going to be exactly the same, but opposite. So then it wouldn't be exactly the same, wouldn't? But is you're going to have a very similar formula. We know that boiling point is the temperature at which vapor pressure is equal to atmospheric pressure. That's why as you go up a mountain and atmospheric pressure decreases, that means that your boiling point becomes lower because the atmospheric pressure is being lowered. So change in vapor pressure is going to cause a change in boiling point. The vapor pressure of a non-volatile solution is lower than the vapor pressure of the pure solvent. That's what I started talking about first. So that means that more heat is going to be required to raise the vapor pressure of the solution. So if you have fewer molecules that are escaping into the gas phase, then that means you're going to have to raise the temperature to try to have more liquid molecules boiling and becoming gas. So this means that the boiling point of a solution is higher than the boiling point of the pure solvent. So just like we have Kf for freezing point, we have Kb, the molal boiling point constant. And for water, it happens to be 0.51 degrees C per molal. Skip right past it. The boiling point constant for water, sorry, the molal boiling point constant for water is 0.51 degrees C per molal concentration. Now the difference here is going to be, we're going to have the same, where is it? The same formula, but we have TB and KB instead. And now is going to be an important distinction between boiling point elevation and its new boiling point, because you're going to have to add 100 to your delta TB because water boils at 100 degrees. So again, using the same exact method, what is the boiling point elevation of a solution made from 20 grams of a non-electrolyte solute and 400 grams of water? The molar mass of the solute is 62 grams per mole. Now, again, I can use the term a non-electrolyte solute without telling you what it is because it doesn't matter what it is. It only matters what the concentration is. So you are given the solute mass and the molar mass of that solute, so you can change it to moles. You're also given the solvent mass and identity. The reason why the identity matters here is because you have to know what the normal boiling temperature of the pure solvent is. Your unknown for this question is only calculating boiling point elevation. You don't have to worry about the new boiling point. Excuse me, I'm like boring myself. So the plan is changing the mass of the solute to moles, calculating the molality, and then again, using the same equation. Pretty nice how the equation is the same, right? The only difference is your KB is going to be different than your KF. So 20.1 grams of solute changes to 0.324 moles of solute. Then you're going to divide that per 0.4 kilograms. They've done it the long way. I wouldn't do it that long way. And you get 0.81 molal. Put that into your delta TB equation, and you get 0.41 degrees C. So the change in your boiling point is going to be 0.41 degrees Celsius. Oh, sorry. If I were to ask you, what's the new boiling point of the solution? You would say 100.41 degrees Celsius. Okay, I don't know why those things went. Oh, I forget to mention why we care. So for freezing point depression, why we care, oops, my goodness. Oh, weird, I don't talk about it in here. It must come up in a worksheet or something, but I will mention it here. The reason why we care and why we use these things is because for freezing point depression, this is, and you guys wouldn't know because it doesn't ever freeze here in Thailand, but if you're ever in a country where it does freeze, during the wintertime, because I grew up with this, during the wintertime, you have salt trucks that drive down roads, and they sprinkle rock salt all over the roads. And this is to depress the freezing point of the water during the wintertime, so you don't have ice on the roads. It also helps to melt any of the ice that's on roads, because if you ever look up videos on YouTube of black ice is basically when you have roads and the road's completely covered in ice, but you can't see it. I don't know what I was watching, like fail videos or something the other day, and like there was one video of a giant pickup truck that was literally like going like just sliding down the road sideways, completely sideways, because of black ice, and you could not tell that there was ice on the road at all. So that is an application of freezing point depression. If you can add salt to the road. Now, the reason why salt is even better, and here's why I talked about being able to identify moles of ions. And the reason why we always say non-electrolyte solute is because if we dissociate salt, we get 2 moles of ions. So if I have a 1 molal solution of salt that is not equal to 1 molal solution of sodium ions and chloride ions, it would actually be 2, because for ionic compounds, you have to account for the fact that they dissociate and they form moles of ions. So 1 mole of NaCl is going to be 2 moles of ions. If on a worksheet, I ever ask you to calculate freezing point depression or boiling point elevation for electrolytes, you have to account for the fact that they dissociate in solution and form multiple moles of ions. I really wish Keynote had an eraser. And the other thing, boiling point elevation. Another application of freezing point depression is an antifreeze. In countries that get cold, you have to put antifreeze in your car. I think it goes in the radiator. because like countries where it doesn't ever get cold, you can just add water to your radiator. The radiator, if you don't know, is, and if I remember this right, the radiator is what cools your engine down of your car. And usually they use water or antifreeze. And the reason why they use antifreeze is because you don't want that water in your radiator to freeze during the winter. So antifreeze is a solution, I think it's ethylene glycol. And so then that means that the freezing point is going to be depressed and your radiator won't freeze during the wintertime. The other side of that is also boiling point. So in cars in the desert, they also use antifreeze, even though it's not for freezing, it's for boiling, because if you raise the boiling point, it also means that like if you're in the Sahara and your engine gets really hot, that means that your radiator fluid won't evaporate, it won't boil away because you're using antifreeze in it, even though it's like opposite, it should be anti-boiling, I don't know, but it's the same solution anyway. Okay, so practice problem, and I've got 9 minutes left. A solution contains 50 grams of sucrose dissolved in 500 grams of water. What is the boiling point elevation? Again, it doesn't ask you for the new boiling point, only boiling point elevation, which is delta TB. So we use the same equation, not A. Delta TB equals KB times M. So we have to change 500 grams of sucrose into moles. So we go 50 grams C12H22O11. Now sucrose, I don't know, but I think it was 342 if I remember correctly from a previous slide. And I'll just round that off. So that cuts. Get my calculator out. 50 divided by 342. That can't be right. Didn't put that in right. 342. 0.15, let's say, moles, and we're going to put that over 0.5 kg, and we get 0.29 molal. So delta TB equals 0.51. Again, that's a constant. 0.29 molal, 0.51, and we get 0.15 degrees C. So that's the change in boiling point. That means that the solution will boil at 100.15 degrees.